On a Monday at the end of June, in a tunnel beneath the border of France and Switzerland, the largest machine ever built went quiet. For most of 2 decades, the Large Hadron Collider at CERN had been slamming protons together at nearly the speed of light, and inside those collisions it kept finding things no one had ever held before. Only months before it powered down, it turned up a brand new particle, a heavy cousin of the proton that had never once been seen. That is the strange thing about this machine. It keeps handing the world over in pieces steadily, one collision at a time, and even the people who built it are still catching up to what those collisions hold. Tonight, we go down into the ring and we look slowly at what it found. On the last Monday of June, in the year 2026, a machine that had run almost without pause for years came quietly to a stop. It sits in a tunnel that runs in a great circle beneath the countryside near Geneva. The tunnel is silent now, in a way it has not been for a very long time. For most of 2 decades, beams of particles raced around that ring day and night, and now they do not. The people who run it call this moment the start of Long Shutdown 3. It is a planned pause, not a breakdown, and it is meant to last about 4 years. But standing at the surface, above the sealed shaft that drops down to the ring, you would not guess any of that. You would see low buildings, a car park, and the flat green fields where France meets Switzerland. The drama is all underground, and now it has gone still. To picture what has stopped, imagine a hollow ring buried about 100 meters down, wide enough to walk through, and 27 kilometers the whole way round. That is the size of a small city. Inside it, until a few days ago, 2 thin streams of protons flew in opposite directions. Each stream lapped the ring more than 11,000 times every second. They moved so close to the speed of light that the gap between their speed and light itself hardly has a name. At 4 points around the ring, those 2 streams were steered straight into each other, so that protons met head-on. The machine is called the Large Hadron Collider, and it belongs to CERN, the European Laboratory for Particle Physics. The name sounds grand, and the thing itself is grand. It is the largest and most powerful machine of its kind that anyone has ever built. Yet its purpose is oddly simple to say out loud. It takes the smallest pieces of matter we know how to handle, speeds them up as much as we can, crashes them together, and watches very closely what comes out. What comes out is the whole reason for the machine. In the sliver of a second when 2 protons collide, their energy can turn into new particles that did not exist the moment before. Some of those particles have never been seen anywhere else in the universe. The collider is, in that sense, a way of asking a question and reading the answer in the wreckage, and in the months before it powered down it gave some of its clearest answers yet. That is what draws us here tonight. Not the machine alone, though the machine is a marvel, but the things it found inside itself. A brand new particle, heavier than a proton, that no one had ever held before. Faint signs that our best theory of matter may not be the whole story. Even a glimpse of one of the strangest features of the quantum world, seen at an energy far beyond anything a tabletop experiment had ever reached. For now, the ring rests. The great magnets are warming slowly toward room temperature. Crews are getting ready to open sections that have been sealed and cold for years. When it wakes again, near the end of the decade, it will be a stronger machine than before. But before we follow it forward, it is worth going back down into the dark. We want to understand what this ring really is, how it works, and why anyone would build a circle of magnets the size of a city just to make 2 specks of matter touch. The tunnel came first, and it was not dug for this machine at all. In the 1980s, engineers carved a circular tunnel under the border near Geneva for an earlier collider that fired electrons around the same loop. When that machine finished its work, the tunnel stayed, and the Large Hadron Collider was built to fill it. That is why the ring is exactly the size it is. It inherited its shape from the machine that came before. The tunnel runs about 100 meters underground, deep enough that the countryside above carries on as if nothing were there. Cows graze over parts of it. a regional airport sits near one edge. The ring is not a perfect circle, but a rounded shape made of long curved arcs joined by shorter straight sections. All the way round, it measures 27 kilometres. If you tried to walk it at an easy pace, it would take you the better part of a morning. Inside the tunnel, the important part is thinner than you might expect. The beams do not travel through open air. They run inside two narrow metal pipes, each about the width of a garden hose, held side by side. One pipe carries protons one way around the ring, and the other carries protons the other way. The two pipes only join at the 4 points where the beams are brought together to collide. Those pipes hold one of the emptiest spaces ever made by people. To keep the flying protons from bumping into stray air molecules, the pipes are pumped down to an extreme vacuum, emptier than the space between the Earth and the Moon. A single stray gas molecule could knock a proton off course, so the engineers take the air away almost entirely. The protons then have a clear road, lap after lap, with almost nothing to hit until they are meant to. The ring straddles two countries, and that is not just a piece of trivia. CERN itself was founded in the 1950s by a group of European nations who had lived through a war and wanted to build something together instead. The laboratory grew into a place where thousands of scientists from all over the world share one set of machines. The collider reflects that. A proton on its journey may cross under French soil and Swiss soil several times in a single second, and no one on the beam would care. Above ground, the laboratory looks less like a temple of physics and more like a busy campus. There are offices, workshops, and a famous corridor lined with the names of experiments. Trucks move parts between buildings, but every so often a lift carries a small group of people down a shaft, past thick doors, into the cool of the tunnel, where the ring waits in the dark. The scale is the thing that stays with you. We're used to thinking of physics as something done on a bench, with small instruments you can hold. Here, to study the smallest objects we know, people built one of the largest structures on the planet. The reason for that size is not decoration. To learn about the tiniest pieces of matter, you have to hit them very hard, and hitting them hard takes a very long runway. The next chapters are about that runway, and about how a proton is coaxed up to nearly the speed of light before it ever reaches the ring. A proton does not start its journey fast. It starts as part of an ordinary bottle of hydrogen gas. Hydrogen is the simplest element, and each of its atoms is little more than one proton with a single electron circling it. At CERN, the gas is fed into a small device that strips the electrons away, leaving bare protons behind. Those loose protons are the raw material for everything that follows. From there, the protons do not go straight into the Great Ring. They pass through a chain of smaller machines, each one handing off to the next like runners in a relay. The first is a straight accelerator, a kind of launch track that gives the protons their initial push. Then they enter a series of ever larger rings, each one older and smaller than the collider itself, each one adding more speed. Some of these machines are decades old, and were once the most powerful in the world in their own right. Now they serve as the opening stages of a longer climb. The reason for this relay is practical. You cannot take a slow proton and force it up to full speed in one step. The magnets that steer a fast proton are far too strong for a slow one, and the magnets that hold a slow proton are far too weak for a fast one. So each machine works within its own range, brings the protons up to a certain speed, and then passes them to a bigger machine built for the next stretch. By the time the protons reach the collider, they're already moving at a large fraction of the speed of light. The final ring only has to push them the rest of the way. The protons do not travel as a smooth, endless stream. They're gathered into tight little clumps called bunches. Each bunch holds something like 100 billion protons packed into a space narrower than a human hair. A full beam is a long train of these bunches, spaced evenly around the ring, with gaps between them. When two beams are steered into each other, it is really two trains of bunches passing through one another, bunch meeting bunch, over and over. To keep the protons moving faster and faster, the collider uses radio waves. At certain points around the ring sit special cavities that hold an electric field, switching back and forth in perfect time with the passing bunches. Each time a bunch flies through, the field gives it a small forward kick, the way a hand on a swing adds a little push at just the right instant. One kick alone does almost nothing, but a bunch takes that kick more than 11,000 times a second, lap after lap, and the tiny pushes add up until the protons are moving as fast as the machine can drive them. There is a strange limit hiding in all this. Nothing with mass can quite reach the speed of light, no matter how hard you push it. So as the protons approach that speed, the extra energy stops making them noticeably faster. Instead, it piles up inside them as sheer energy of motion, the very energy that will matter most when two of them finally collide. A proton in the full beam carries roughly the motion energy of a flying mosquito, all crammed into a single speck far smaller than an atom. That concentration is the point. In the next chapter, we follow those protons into the ring itself and meet the magnets that bend their path. Once the protons enter the main ring, something has to keep them going in a circle. Left alone, a fast proton flies in a straight line. To curve its path around 27 kilometers of tunnel, the collider leans on magnets, and a great many of them. The most important are the bending magnets, called dipole magnets. There are 1,232 of them spaced around the ring, each about 15 meters long and weighing as much as a couple of large cars. Their whole job is to nudge the beam sideways, again and again, so that a straight-flying proton is gently curved into a loop. An ordinary magnet, the kind that holds a note to a refrigerator, would be nowhere near strong enough. To bend protons moving this fast, the magnets have to be extraordinarily powerful, and that is where the deep cold comes in. The magnets are wound from special cables that carry electricity without any resistance at all, but only when they are made very, very cold. This trick is called superconductivity, and it lets a magnet run enormous currents without overheating or wasting energy. To reach that state, the magnets are chilled with liquid helium down to about 1.9 degrees above absolute zero. Absolute zero is the lowest temperature there can be, the point where all warmth has been drained away. The magnets sit just a hair above it. To put that in perspective, the empty space between the stars is warmer, kept faintly warm by the afterglow of the Big Bang at around 2.7 degrees above absolute zero. The heart of the collider is colder than deep space. It is one of the coldest large places in the known universe, and people made it on purpose under a field in Europe. Keeping something that cold, that large, is its own quiet feat of engineering. Miles of piping carry liquid helium through the magnets and around the ring, held in place by layers of insulation and vacuum that block heat from creeping in. The whole cold section behaves like a single enormous refrigerator wrapped around a city-sized loop. Cooling it down from room temperature takes weeks. Warming it safely takes weeks as well, which is part of why a shutdown is measured in years rather than days. The bending magnets are not the only kind. Between them sit smaller focusing magnets, whose task is to squeeze the beam and keep it narrow. Over a long journey, a bunch of protons tends to spread out, the way a beam of light slowly widens. The focusing magnets pinch it back together, so the protons stay in a tight thread instead of smearing against the pipe walls. Near the collision points, still stronger magnets squeeze the beam down hard, packing the protons close so that more of them will actually meet when two bunches cross. All of this depends on the magnets holding their delicate cold state without fail. If a superconducting magnet warms up even slightly in the wrong spot, it can suddenly lose its perfect state and dump its energy as heat. The engineers call this a quench, and the machine is watched constantly to catch the earliest hint of one. Early in the collider's life, a fault of this kind damaged a stretch of magnets and set the whole project back by more than a year. Since then, the safeguards have been rebuilt and the machine has run for long, steady stretches. With the magnets cold and the beams tight, the protons are finally ready for the only thing they were sped up to do, which is to meet. The collision itself is almost too fast and too small to imagine, so it helps to slow it down in the mind. Two trains of proton bunches are flying toward each other from opposite directions, each moving at nearly the speed of light. At one of the four meeting points, the focusing magnets have squeezed both beams down to threads far thinner than a hair. The machine then tips the two beams so their paths cross. For a brief instant, one bunch passes clean through the other. Even then, most of the protons miss. A bunch is mostly empty space, the way a swarm of gnats is mostly empty air, so the two clouds slip through each other and only a handful of protons actually strike head-on. That is fine. A handful is enough. Out of the trillions of protons crossing every second, the machine produces something like 1 billion true collisions in that same second, spread across all 4 meeting points. From those, the interesting events are rare, and the rarest are the whole prize. When 2 protons do meet squarely, the energy of that impact is enormous for something so small. Each beam carries protons at an energy the physicists measure in trillions of electron volts, and in the most recent runs, the 2 beams together reached about 13.6 trillion electron volts in a single collision. An electron volt is a tiny unit, the energy an electron picks up crossing a small battery. Piling trillions of them into one proton, then smashing 2 such protons together, concentrates a startling amount of energy into a space smaller than an atom. Here is where the collider does its real trick, and it rests on the most famous idea in physics. Energy and mass are 2 forms of the same thing, tied together by the simple relation that energy equals mass times the speed of light squared. Because the speed of light is such a large number, a small amount of mass holds a great deal of energy, and run the other way, a great deal of energy can become new mass. When 2 protons collide hard enough, their motion energy does not simply scatter. Some of it condenses into brand new particles, heavier than the protons that made them, particles that were not present the instant before the crash. This is why the collider is built for energy above all else. To make a heavy particle, you need enough energy to pay for its mass. The heavier the particle you hope to create, the harder you must hit. Many of the particles physicists want to study are far heavier than a proton and do not exist naturally anywhere nearby. The only way to see them is to make them, briefly, in a collision violent enough to bring them into being. The particles born this way rarely last. Most of them fall apart almost at once, in far less than 1/1000th of a second, decaying into lighter, more familiar particles that fly outward from the crash. Those outgoing pieces are what the detectors actually catch. A physicist almost never sees the heavy particle itself. Instead, they see its debris spraying out, and from that spray they reconstruct what must have existed for the briefest moment at the centre. So a single collision is a small act of creation and destruction, over before any clock could mark it. To read what happened, you need instruments wrapped tightly around the point of impact, built to catch every fragment. Those instruments are the great detectors, and there are 4 of them. They are the next place we go. Around the ring, at the 4 points where the beams cross, sit 4 enormous detectors. Each is a cathedral of metal and wire built to catch the spray of particles from the collisions at its centre. They have short names that began as descriptions of their design, and over the years the names simply became the names. There are 4 big experiments, and each one looks at the collisions with a different question in mind. The 2 largest are called Atlas and CMS. Both are general-purpose machines, built to catch as much as possible from every collision and to search widely for whatever might appear. Atlas is the size of a large building, tall enough to hold a cathedral nave inside it, and yet it is packed so full of detecting layers that there is barely room to move. CMS is more compact but even heavier, built around a single gigantic magnet, and it weighs more than the iron in a large tower. The 2 are built by separate teams on purpose. If both machines, working independently, see the same thing, then the result is far harder to doubt. Their friendly rivalry is part of how the laboratory checks itself. The 3rd detector is called Alice, and it was built for a different kind of collision. Instead of protons, the collider can also fire the nuclei of lead atoms at each other, which are far heavier and messier. When 2 lead nuclei collide, they create a tiny, unimaginably hot droplet of matter unlike anything in ordinary experience, and Alice is designed to study that droplet. It is tuned to make sense of the thousands of particles that pour out of a heavy collision where the simpler detectors would be overwhelmed. We will come back to what that droplet is, because it is one of the strangest things the machine makes. The fourth big detector is called LHCb, where the small letter B stands for a heavy kind of quark once nicknamed Beauty. Unlike Atlas and CMS, this one does not try to surround the collision on every side. It is stretched out mostly in one direction, along the beam, because the particles it cares about tend to fly forward after a crash. LHCb specializes in rare, delicate measurements, watching how certain heavy particles are born and how they fall apart. It is this experiment that has found most of the new particles we will meet later, and it is the one that recently caught the freshest surprise of all. Alongside these four sit several smaller experiments tucked into corners of the ring, each with a narrow and specific task. One of them, a modest detector far down the tunnel from a collision point, managed to catch something no collider had caught before, and we'll get to it in its own chapter. The laboratory is layered like this, with a few giants and many specialists, all fed by the same beams. What unites them is the challenge they share. At each meeting point, collisions happen tens of millions of times a second, and every collision throws out a burst of particles in all directions. To learn anything, a detector has to record where each particle went, how fast, how heavy, and what kind it was, and it has to do this over and over without pause. That is a staggering amount of information arriving faster than any storeroom could ever hold. How a detector sees it all, and how it decides what is worth keeping out of that torrent, is a story in itself, and it is where we turn next. A detector at the collider is really a camera, though not the kind you hold. It is built in layers, like the rings of an onion, wrapped snugly around the point where the beams cross. When particles fly outward from a collision, they pass through one layer after another, and each layer is designed to notice something different about them. Put together, the layers build a full picture of the burst, telling the physicists what came out of the crash and where each piece went. The innermost layers sit closest to the collision and are the most delicate. They are trackers, made of silicon, and their job is to trace the fine, curving paths of charged particles as they fly through. A magnetic field bends those paths, and the amount of bending reveals how much momentum each particle carries, the way a strong wind bends a light branch more than a heavy one. Around the trackers sit heavier layers that stop particles more forcefully and measure their energy, catching the sprays of lighter debris. The outermost layers are usually built to catch a particle called the muon, a heavier cousin of the electron that slips through everything else and betrays itself only at the very edge. The speed of all this is the hard part. At full running, bunches cross inside each detector about 40 million times every second. One of the engineers who built part of the newest tracker described his detector plainly as a camera that takes a photograph 40 million times a second. Every one of those crossings can hold several collisions, and every collision throws out its own spray. If the machine tried to save all of it, it would fill the world's storerooms in minutes and drown in its own data. So the detectors do not keep everything. They cannot. Instead, they lean on a system called the trigger, which acts like a lightning-fast editor. In the first instant after a crossing, simple electronics glance at the raw signals and throw away the overwhelming majority that look ordinary. A slower stage of computers then studies what survives and keeps only the events that look genuinely interesting, the ones with the telltale signs of something rare. Out of the 40 million crossings each second, only a small handful are written down and stored. Everything else is gone forever, unlooked at, because it had to be. This is a quiet gamble at the heart of the whole enterprise. The physicists decide in advance what an interesting event should look like, and they build those choices into the trigger. If they guess wrong, if the thing they most want to find leaves a signature they never told the trigger to save, then it could be created millions of times and thrown away every time unseen. Much care goes into making the trigger broad enough not to miss a surprise while still sharp enough to survive the flood. What does survive is enormous. Even after all that filtering, the 4 experiments together record a staggering amount of data, enough to fill vast banks of computers spread across the globe. No single centre could handle it. Instead, the laboratory built a worldwide network of computing sites that share the load, passing the data outward so that thousands of physicists in dozens of countries can each take a piece and study it. A discovery made in Geneva may first be spotted on a screen far away. All of this, the layered cameras, the trigger, the global web of computers, exist to answer one question about any given event. Did we just see something real, or did we fool ourselves? That question turns out to have a strict and beautiful answer, and it is the subject of the next chapter. Physics at a collider is a hunt for the rare, and the rare is easy to imagine into being. Out of trillions upon trillions of collisions, unusual patterns will show up now and then purely by chance, the way a long enough run of coin flips will eventually turn up a surprising streak. So the field has learned to be strict with itself. Before anyone announces a discovery, they must show that what they saw is very unlikely to be a fluke, and they measure that unlikeliness with a single yardstick. That yardstick is often described in terms of a bump on a graph. When physicists search for a new particle, they usually plot how many collisions produced a certain result at each possible energy. Most of that plot is background, a smooth expected slope from ordinary well-understood processes. A new particle would show itself as an excess piled up at one particular energy, a bump rising above the smooth background at the spot that matches its mass. The taller and cleaner the bump, the more seriously it is taken. The strength of a bump is measured in units the physicists call sigma, a word for how far a result stands out from what chance alone would produce. A result of 2 or 3 sigma is mildly interesting, but often fades away as more data comes in. The field has set a firm line at 5 sigma. A 5 sigma result means that, if there were really nothing there, a fluctuation this large would happen only about once in several million tries. Only when a signal crosses that line do the collaborations allow themselves to use the word discovery. Anything short of it is called, carefully, an indication or a hint. This rule exists because the history of the field is littered with bumps that looked thrilling and then melted away. A promising signal appears in an early batch of data, excitement spreads, and then more collisions arrive and the bump flattens back into the background, revealing itself as noise all along. The 5 sigma line is the community's hard-won defense against its own hope. It has been crossed for the great discoveries and missed, sometimes narrowly, for many hopeful signals that came to nothing. To keep hope from tilting the scales, the experiments often work blind. In a blind analysis, the physicists build and test their entire method, while hiding the very region of data where the answer would appear. They tune everything on the surrounding uninteresting parts, lock their choices in place, and only at the end do they lift the veil and look at the real result. That way they cannot, even without meaning to, keep nudging their analysis until it shows them what they wish were true. It is a discipline of not peeking, and it is taken seriously. There is also the matter of 2 experiments. Because Atlas and CMS were built separately and run by separate teams, a claim carries far more weight when both of them see the same thing on their own. One machine alone might harbour a flaw that fakes a signal. 2 machines, independently designed, are unlikely to share the same flaw. When both announce the same bump at the same mass, the case becomes very strong. So a discovery at the collider is not a single dramatic flash on a screen. It is a slow, guarded process, built out of statistics, hidden data, cross-checks, and the agreement of rival teams. The moment of announcement is really the visible tip of years of careful doubt. Once, that whole machinery of caution swung into place around one particular bump, near a mass that theorists had waited half a century to reach, and it gave the collider its most famous day. On the 4th of July, in the year 2012, a lecture hall at CERN filled long before dawn. Young physicists had slept in the corridor overnight to claim a seat. Word had spread that the 2 big experiments, Atlas and CMS, were about to present something important, and the room was thick with the sense that a long wait was ending. Sitting in the audience was an elderly man named Peter Higgs, who had helped predict nearly 50 years earlier the very thing about to be announced. One after another, the leaders of the two experiments walked through their results. Each showed the same kind of picture: a smooth background, and rising out of it a bump at a mass just under 130 times the mass of a proton. Both teams, working entirely on their own, had found an excess at almost exactly the same place. Both had crossed, or all but crossed, the 5 sigma line. When the second talk finished and the meaning settled in, the room broke into applause, and Peter Higgs was seen to wipe his eyes. The bump was the Higgs boson, a particle whose existence had been proposed in the 1960s and hunted ever since. It was the last missing piece of the long-standing theory of particles, the one prediction that had stubbornly resisted being caught. Machines before the collider had searched for it and failed, narrowing the range where it could hide without ever cornering it. The Large Hadron Collider had been built in large part to settle the question one way or the other. On that summer morning it did. Finding the Higgs was so hard because the particle is both heavy and desperately short-lived. It cannot simply be scooped up. It must be made in a violent collision, and then it vanishes almost instantly into lighter particles long before any instrument could touch it. What the detectors actually recorded were those decay products, flying outward in particular patterns. By adding up the energy and direction of the debris, the physicists could reconstruct the fleeting parent that must have existed at the centre, and see it appear again and again at the same telltale mass. That repetition, that steady bump, was the proof. The two teams had also guarded against fooling themselves in exactly the ways the field demands. They had worked with parts of their data hidden, locked their methods before looking, and compared results only at the end. Above all, they had each other. Two separate machines, two separate collaborations, had landed on the same particle at the same mass. That agreement is what turned a striking graph into a genuine discovery. The following year, the prize that often marks such moments went to two of the theorists who had predicted the particle, Peter Higgs and François Englert. A third, who had shared in the original idea, Robert Brute, had died 2 years before, and so could not be named. A quiet reminder of how long the wait had been. The particle they described had taken almost half a century to travel from a line of equations to a signal on a screen. The discovery mattered far beyond the joy in that lecture hall. The Higgs boson was not just one more particle added to a list. It was the visible sign of something deeper, an invisible field spread through all of space, tied to the very reason that matter has mass at all. To understand why its arrival was so anticipated, we have to ask a question that sounds almost too simple to be scientific. Why does anything weigh what it weighs? That is where we go next. Ask why an object is heavy, and the everyday answer is that it is made of a lot of stuff. But go deep enough, down to the smallest particles, and the question turns strange. What gives a single, indivisible particle its mass when there is nothing inside it to add up? For a long time, the best theory of particles had an awkward gap right here. Its equations worked beautifully only if the most basic particles had no mass at all, which was plainly false, since particles like the electron clearly do weigh something. In the 1960s, several physicists working separately came up with a way out. Suppose, they said, that all of space is filled with an invisible field, present everywhere, even in the emptiest vacuum. Particles moving through this field would feel a kind of drag, and that drag would show up as mass. A particle that interacts strongly with the field would feel a lot of drag and be heavy. A particle that barely notices the field would feel almost none and be light. A particle that ignores it entirely, like the particle of light, would stay massless and race along at full speed. This invisible field came to be called the Higgs field, after one of the physicists who described it, though others reached similar ideas at nearly the same time. It is worth being careful about the popular picture of it. People often say the field is like a thick syrup that everything wades through, and that image captures the idea of drag, but it can mislead. the field does not slow a particle down forever or bring it to a stop. Instead, its constant presence is what makes certain particles behave as though they have weight in the first place, giving them the property we call mass rather than simply breaking them. Here is the part that made the idea testable. According to the theory, if such a field truly fills space, then giving it a hard enough jolt should make it ripple, and a ripple in the field would appear to us as a particle. That particle is the Higgs boson. So the boson found in 2012 was not the field itself, which is everywhere and cannot be held. It was a single ripple, a disturbance in the field, knocked loose by the energy of a collision. Seeing that ripple was the way to prove the field was real. This matters because mass is not a small detail. Without the Higgs field, the theory says, the basic building blocks of ordinary matter would have no mass and would fly about at the speed of light, unable to settle into atoms. There would be no atoms, no chemistry, no stars, no planets, and no one to wonder about any of it. The quiet, invisible field is part of why the universe is able to hold together into solid things at all. It is not the whole story of mass, since much of the weight of a proton comes from the energy of the forces inside it rather than from the field. But for the fundamental particles themselves, the field is the source. For decades, this was a beautiful guess with no direct proof. The field, if it existed, was silent and hidden, and the only way to confirm it was to shake it hard enough to produce a ripple, then catch that ripple before it vanished. That took a machine as powerful as the collider. When the ripple finally appeared, it confirmed an idea that had been waiting 50 years, and it did something more. It gave physicists a brand new object to study, one they could now make on purpose, over and over, to test whether it behaved exactly as the theory said. That is the next part of the story. Making a Higgs boson is not easy, even for a machine built to do it. The particle is rare. Out of every so many collisions, only a tiny fraction produce one at all, and the machine has to run for a long time to gather enough. Across all its years of operation, the collider produced something like 55 million Higgs bosons. That sounds like a great many, and it is, until you remember how many collisions it took to make them. Against the trillions upon trillions of proton crossings, 55 million is a thin harvest, gathered patiently over more than a decade. Even once a Higgs is made, it does not linger to be examined. It falls apart almost the instant it appears, in a time far too short for any instrument to catch it whole. So physicists study it the same way they discovered it, by its debris. A Higgs can decay in several different ways, into different sets of lighter particles, and each way leaves its own signature in the detectors. By collecting many events and sorting them by how the parent fell apart, the physicists slowly build a portrait of the particle they never see directly. This is where a large pile of Higgs bosons becomes precious. With only a handful, you can say the particle exists. With millions, you can begin to ask whether it behaves exactly as the theory predicts. The theory makes sharp claims about how often the Higgs should decay each way, and how strongly it should attach to each other kind of particle. Every one of those numbers is a test. If the real particle matched the predictions in every detail, the theory would stand. If it strayed, even slightly, that gap could be the first clue to something new. So the years after the discovery became years of careful measurement. The experiments checked how strongly the Higgs couples to heavy particles and to lighter ones, and the pattern held up remarkably well. One of the harder cases was its link to a particle called the muon, that heavier cousin of the electron. The Higgs attaches only weakly to it, so that decay is very rare and hard to pick out from the background. Catching it took enormous amounts of data, and even then the evidence came in slowly, as a faint but growing signal rather than a sudden bump. Every measurement so far has told a slightly deflating and deeply impressive story at once. The Higgs boson has behaved, within the precision available, just as the 50-year-old theory said it should. There has been no clear crack, no obvious surprise hiding in how it decays. For a theory to predict a brand new particle, and then have that particle turn up and act exactly as promised, is a triumph. It is also, for physicists hungry to find something beyond their current map, a little frustrating. the map keeps being right. But precision has limits, and the limits are set by how many Higgs bosons you have to study. 55 million is enough to confirm the broad picture. It is not nearly enough to catch small deviations, the kind that might only show up in the rarest decays, or in events where two Higgs bosons are made at once, something the machine has barely managed to glimpse. To hunt for those, physicists need far more of the particle, which is one of the main reasons the collider is now being rebuilt to make many times as many. The Higgs is only one piece, though, of a much larger picture that the collider was built to test. That picture has a name, and it is the framework against which every result is measured. To see why a small deviation would matter so much, we need to step back and look at the whole map of particles and forces. That map is where we go next. Physicists have a single picture that ties together almost everything they know about the smallest pieces of the world. They call it the Standard Model, a plain name for a remarkable achievement. It is a compact catalogue of the fundamental particles, the ones that cannot be split into anything smaller, along with the rules for how they push and pull on one another. Nearly every result from the collider is measured against this picture, either confirming it or straining against it. The particles in the Standard Model fall into two broad families. The first are the particles of matter, the ones that make up substance. Among them are the quarks, which we will meet closely in a moment, and a lighter group that includes the familiar electron and the faint elusive particle called the neutrino. Ordinary matter, the stuff of you and the ground and the stars, is built almost entirely from just a few of these, mainly two kinds of quark and the electron. The rest are heavier versions that appear only briefly, made in collisions or in the violent places of the cosmos, and then decay. The second family are the force carriers. In this picture, a force is not a mysterious action at a distance, but something passed between particles, carried by other particles that flit between them. The particle of light, the photon, carries the electric and magnetic force. A pair of heavier particles carry the so-called weak force, which governs certain kinds of radioactive decay. And a particle called the gluon carries the strong force, the powerful glue that binds quarks together. The Higgs boson sits a little apart from these, tied to the field that gives many of the others their mass. Between them, these particles account for three of the four known forces of nature. There is electromagnetism, which holds atoms together and lights the world. There is the weak force, quiet and short-ranged, which drives the reactions that power the sun. And there is the strong force, the most powerful of all, which we will spend time on because it lies behind so much of what the collider finds. Each has its carrier, each has its rules, and the Standard Model describes them with an accuracy that is genuinely hard to overstate. There is a glaring gap, and physicists are the first to point it out. The fourth force, gravity, is missing from the picture entirely. The Standard Model has no particle for gravity that fits neatly with the rest, and no accepted way to fold it in. For everyday purposes, this hardly matters, since gravity is far too weak to notice between two tiny particles, but it means the beautiful map is known to be incomplete. A theory that leaves out one of the four great forces cannot be the final word. There are other gaps as well, and they are part of why a machine like the collider keeps running. The Standard Model says nothing about the invisible matter that seems to hold galaxies together, nor about why the universe is made of matter and almost no antimatter. It has no room for these things, and yet the evidence for them is strong. So the map is prized and doubted at the same time. It predicts the results of experiment after experiment to astonishing precision, and it plainly cannot be everything. This is the setting for the whole search. Every measurement at the collider is, in a sense, a test of whether the Standard Model still holds, or whether some small disagreement will finally open a door to what lies beyond it. To go deeper into that search, we start with the pieces of the map that the collider studies most directly, the quarks, and with the simple rule that governs how they combine. Deep inside every proton and every neutron sit even smaller particles called quarks. They are among the truly fundamental pieces of matter, with nothing known to lie inside them. What makes quarks unusual is that they are never found wandering alone. Wherever you look, they come bound together in small groups, locked inside larger particles, and no experiment has ever isolated a single free quark to hold on its own. Understanding why is one of the deep threads running through the collider's work. Quarks come in 6 kinds, which physicists whimsically call flavors. The 2 lightest are named up and down, and they are the ones that build ordinary matter. The other 4 are heavier and named charm, strange, top, and bottom, the last of which was once nicknamed beauty. These heavier flavors do not last. They are made in violent collisions or in the extreme corners of the universe, and they decay almost at once into the lighter kinds. Only the up and the down quark are stable enough to make up the familiar world. The rule for how quarks combine is neat. For most of the history of the subject, quarks were seen to gather in just 2 arrangements. 3 quarks bound together form the family of particles called baryons, and the proton and neutron are the 2 everyone knows. A proton is 2 up quarks and 1 down quark. A neutron is 1 up quark and 2 down quarks. That small difference in their quark content is enough to give them slightly different properties, and to shape the chemistry of every atom. The other arrangement pairs a quark with an antiquark, a partner from the mirror world of antimatter. Such a pair forms a particle called a meson. Mesons are lighter and far less stable than protons and neutrons, flickering into existence in collisions and decaying quickly. They played a large part in the early days of particle physics, when new ones seemed to turn up faster than anyone could name them. Together, baryons and mesons make up the broad class of particles called hadrons, and the collider is, among other things, a factory for hadrons. For decades, these 2 patterns, quarks in threes and quark-antiquark pairs, seem to be the whole story. The underlying theory of the strong force, the rules that bind quarks, did not actually forbid larger groupings. On paper, it allowed for particles made of 4 quarks, or 5, or stranger combinations still. But such things had never been clearly seen, and many physicists half assumed that nature, for reasons not fully understood, simply preferred to keep quarks in 2s and 3s. The exotic possibilities lingered as a question at the edge of the theory. That is the tidy picture the collider inherited, and one of its quiet triumphs has been to complicate it. The machine produces heavy quarks in great numbers, especially the charm and bottom kinds, and it produces them far more often than earlier experiments could. That abundance is exactly what you need to hunt for rare, unusual hadrons, the ones that break the neat rule of 2s and 3s. If 4-quark or 5-quark particles could exist at all, a machine that makes heavy quarks by the billion is the place to catch them, and catch them it did. In the years after it started up, the collider began to turn up hadrons that fit neither the 3-quark nor the pair pattern, particles that seemed to hold 4 quarks, and then 5. Each one was a small shock to the tidy picture, and a gift to the theory of the strong force, which had quietly allowed them all along. The rule of 3s, it turned out, was never a law of nature but only a habit of the particles we happen to know. Breaking it is the story of the next chapter. For a long time, the 4-quark and 5-quark particles lived only in theory, tolerated by the equations but never clearly seen. Hints appeared now and then in earlier experiments, tantalizing bumps that were argued over and never quite settled. What was missing was a machine that made heavy quarks abundantly enough and detectors precise enough to pin the exotic particles down beyond doubt. The collider, and especially the experiment tuned to beauty quarks, turned out to be that machine. The first solid break came with the 4-quark particles, the tetraquarks. Around the middle of the 2010s, the beauty quark experiment confirmed that certain long-disputed bumps really were single particles made of 4 quarks bound together, not 2 ordinary particles loosely stuck side by side. That distinction matters, because a genuine 4-quark particle is a new kind of object, a single knot of the strong force holding 4 pieces at once. Confirming it settled years of argument and opened a door that had only been ajar. Not long after came the 5-quark particles, the pentaquarks, studying the decays of a heavy baryon, the same experiment found clear evidence for a particle carrying 5 quarks at once, again as a true bound object rather than a chance overlap of smaller ones. The signal was strong and clean, and it announced that the exotic hadrons were not a fluke of one measurement, but a real and repeatable feature of nature. Both the 4-quark and the 5-quark families had now been caught. It is worth pausing on how these particles are found, because it is the same patient method behind almost every discovery here. The physicists sift through enormous numbers of collisions, looking at the debris and asking which combinations of outgoing particles cluster together at a particular mass. A real particle shows up as an excess, a bump, standing above the smooth background at the mass that matches it. The exotic hadrons revealed themselves exactly this way, as bumps that refused to go away as more data piled in, and that could not be explained by any ordinary process. What makes these discoveries more than a stamp collection is what they teach about the strong force. That force is the least understood of the forces the Standard Model describes, not because the basic rules are unknown, but because they are so powerful and tangled that working out their consequences is extraordinarily hard. Predicting how quarks will bind and which combinations will hold together pushes the theory to its limits. Every new exotic hadron is a fresh test, a real object whose mass and behaviour the theorists can try to reproduce, and each one sharpens their tools. There is a puzzle inside the exotic particles that physicists are still working through. It is not fully settled how the quarks inside a tetraquark or pentaquark are arranged. In one picture, all 4 or 5 quarks are packed tightly into a single dense clump bound as one. In another, the particle is more like a loosely held pair of ordinary hadrons, 2 smaller knots orbiting each other at a slight distance, almost a tiny molecule of the strong force. Different exotic particles may lean toward different answers, and telling which is which, from the debris alone, is delicate work that continues. What is certain is that the neat old rule has been broken for good. Quarks do not only gather in 2s and 3s, they can, at least fleetingly, form richer combinations, and the collider has caught a growing number of them. The first confirmations were only the beginning. In the years that followed, the exotic family kept growing, with new members that were stranger, longer lived, or arranged in ways no one had seen before. That widening zoo is where we turn next. Once the first tetraquarks and pentaquarks were confirmed, the discoveries did not stop. They came in a steady stream, each adding a new member to a family that had been empty a decade earlier. The beauty quark experiment, sifting ever larger piles of collisions, became the great hunter of exotic hadrons, and its list grew year by year. What had been a daring question at the edge of the theory turned into an active field with a crowded catalogue. One striking find came when the experiment spotted a bump in collisions that produced pairs of a particle called the J psi, itself a bundle of a charm quark and its antimatter partner. The bump pointed to a new tetraquark that appeared to be built entirely from charm quarks and their antiquarks, a heavy all-charm object unlike the lighter exotics found before. It was a reminder that the 4-quark family had many possible members made from different combinations of the 6-quark flavours, and that the collider could reach the heavier, rarer ones. An even more remarkable discovery followed, one that stood out for its stubborn stability. Most exotic particles fall apart almost instantly, but this one, made of 2 charm quarks together with 2 light antiquarks, held together far longer than its cousins, at least 10 times as long as the other exotic states the experiment had found. In the fleeting world of these particles, that is a striking span. The physicists traced its unusual patience to its particular mix of quarks, which happened to leave it with few easy ways to decay. It was the longest-lived piece of exotic matter yet seen. Then, in a single announcement, the experiment reported 3 new particles at once. One was a new kind of pentaquark, a 5-quark particle that was the first of its type found to contain a strange quark among its members. Its signal was extraordinarily strong, standing far above the background at a level well beyond the strict 5 sigma line, so clear that there was no room to doubt it. Alongside it came the first ever pair of tetraquarks seen together, including a new kind of four-quark particle. 3 exotic hadrons delivered in one sitting, each a first of its kind. Every one of these particles is more than a curiosity. Because they are made of unusual quark combinations, they serve as unique testing grounds for the theory of the strong force. A theorist can take the rules of that force and try to predict where each exotic particle should sit, how heavy it should be, and how it should decay. The new hadrons give sharp, real numbers to check those predictions against. Where the theory succeeds, confidence grows. Where it struggles, the physicists learn which of their approximations are failing and why. The variety in the growing zoo is part of its value. Some exotic particles seem to be tight clumps of quarks bound as one. Others behave more like loosely paired hadrons, held at a small distance like a faint molecule. By comparing many different exotic states, their masses, their lifetimes, the way they break apart, physicists can begin to sort out which arrangements nature favours and under what conditions. No single particle answers the question, but a whole catalogue starts to reveal patterns. By the time the machine paused, this catalogue had grown far beyond anything imagined when the first tetraquark was confirmed. Dozens of new hadrons had been added to the list, exotic and ordinary alike, each carefully measured and cross-checked. The sheer number is itself part of the story, a sign of how productive the machine has been at simply finding new pieces of matter. In the next chapter, we take stock of that number, and of what such a haul of new particles tells us about the force that binds them all. By the time the collider fell quiet, the experiments running on its beams had discovered a remarkable haul of new particles. Adding up the hadrons found across the machine's lifetime, the count had climbed past 80 distinct new particles, and by some tallies higher still. Not all of them are exotic. Many are ordinary 3-quark baryons or quark-antiquark mesons that simply had never been made and observed before, heavier or rarer than anything earlier machines could produce. The exotic tetraquarks and pentaquarks are the famous ones, but they sit within a much larger family. 80 new particles is a strange kind of achievement, easy to underrate. There is no single dramatic day attached to it, no lecture hall in tears. It happened gradually, one careful measurement at a time, spread across years and across the different experiments. Yet taken together it represents a vast expansion of the known catalogue of matter. Before the collider, the list of confirmed hadrons had grown slowly over decades. This one machine, in a little over a decade, added a substantial new chapter to it. The reason the collider is so good at this comes back to the heavy quarks. When two protons collide at high energy, they readily produce charm quarks and bottom quarks, the heavier flavours that earlier machines struggled to make in quantity. Those heavy quarks then bind with others to form all manner of hadrons, common and exotic. Because the collider makes them in enormous numbers, even rare combinations show up often enough to be caught, measured, and confirmed. Abundance is what turns a fleeting possibility into a solid discovery. All these particles are, in the end, probes of a single force. The strong force is what binds quarks into hadrons, and it is the hardest of the known forces to calculate with. Its underlying rules are written down and trusted, but those rules are so powerful and self-tangled that predicting the outcome, which combinations bind, how heavy they are, how long they last, becomes fiercely difficult. Each new hadron is a real measured fact that the theory must be able to reproduce. The growing catalogue is a long, detailed exam that the theory of the strong force must sit, question by question. Some of those questions are easy for the theory and some are hard. Ordinary baryons and mesons are largely well understood, and finding new ones mostly fills in expected gaps. The exotic hadrons are harder, because the theory allows them but does not easily predict their details, and because their internal arrangement is still debated. By measuring many of them, physicists build a body of evidence that slowly constrains the possibilities. It is patient, unglamorous work, and it is how a difficult theory is tested in the only way that counts, against reality. There is a broader point worth making about all this counting. It shows that the collider's value is not only in the rare headline discoveries like the Higgs, It is also in this steady output the quiet accumulation of new pieces of matter, each one a small, checkable fact about how the strong force behaves. A machine that produces 80 new particles is not resting on a single triumph. It is doing something closer to cartography, mapping a landscape of matter that had been largely blank, filling it in point by point, and the mapping was still going right up to the end. Some of the most recent additions came in the machine's final stretch of running, after an upgrade had made one of its experiments sharper than ever. The very newest particle, announced only months before the shutdown, is not just another entry on the list. It is a special one, a heavy cousin of the proton itself, and it is the discovery that the title of this story points toward. That is where we go now. In March of the year 2026, only months before the collider would shut down, the beauty quark experiment announced that it had found a brand new particle. It carried a formal name written in Greek letters and subscripts, but its makeup can be said plainly. It is a heavy relative of the proton, built from 2 charm quarks and 1 down quark. The signal for it stood at a strength of 7 standard deviations, comfortably past the 5 sigma line that a discovery demands. There was no serious doubt. Something genuinely new had appeared in the debris. To feel why this find is special, compare it with the proton, the particle at the heart of every atom. A proton is made of 3 quarks, 2 up quarks and 1 down. The new particle keeps the down quark but swaps the 2 light up quarks for 2 heavy charm quarks. Charm quarks are far heavier than up quarks, so the exchange makes the new particle much heavier than a proton, roughly 4 times its mass, while keeping a similar 3-quark structure. It is, in a real sense, a proton's burlier cousin, the same basic pattern rebuilt from heavier parts. There is a nice thread of history in that comparison. The proton was first identified a little over a century ago in a laboratory in Manchester, in the work of Ernest Rutherford and his colleagues, who took apart the atom and found its positive core. The team that led this new discovery included physicists from that same city, building the delicate detector parts that made the measurement possible. A century apart in a line that runs from the proton to its heavy new cousin, the same curiosity keeps pulling at the structure of matter. The new particle mattered for another reason beyond its own strangeness. It was the first discovery made with the upgraded version of the beauty quark detector, whose new components had been installed a few years earlier. Part of that upgrade was a fresh inner tracker, built from silicon and assembled by the physicists themselves, a device one of them described as a camera taking photographs of the collisions 40 million times a second. The new particle was proof that the rebuilt detector worked, and worked beautifully. It showed that the upgrade was already paying off in fresh science. It was also only the second time that a baryon holding 2 heavy quarks had ever been seen. The first, a close relative with 2 charm quarks and an up quark instead of a down, had been found by the same experiment nearly a decade earlier. Now its sibling had appeared, differing only in that single swapped quark. Having both allows physicists to compare them directly, and comparison is where understanding grows. 2 particles that differ by 1 small change are a natural experiment in how the strong force responds to that change. The head of the laboratory, its Director General, called the result a fine example of how experimental upgrades lead straight to new discoveries and set the stage for the more powerful machine to come. The leader of the experiment noted that the find would help theorists test their models of the strong force, the same difficult theory that governs how quarks bind into protons, ordinary hadrons, and the exotic ones alike. The particle was presented at a long-running physics gathering in the mountains to a room that understood exactly what it meant. So the title's promise turns out to be true in a quieter way than a headline might suggest. The collider really did find something inside itself that no one had held before, a heavy new kin of the proton, caught in its final months by a freshly sharpened eye. What that particle teaches, and why a heavier version of the proton is such a useful thing to have, is worth sitting with, and it is where we go next. A heavier version of the proton is more useful than it might first appear. When physicists study the strong force, the great difficulty is that the force is so powerful and so tangled that they cannot simply calculate what it will do. They have to lean on approximations, and the best approximations often work most cleanly when the quarks involved are heavy. A heavy quark moves more slowly and sits more still inside its particle, which makes the mathematics more tractable. So a particle built from two heavy charm quarks is not just a curiosity. It is a rare case where the theory can be pushed toward a real, checkable answer. Think of the new particle as a tiny solar system. The two heavy charm quarks are like a close, slow-moving pair at the centre, and the single light down quark drifts around them like a distant planet. This picture, with a heavy core and a light outer companion, is one that theorists can actually model with some confidence. They can predict roughly how heavy the whole particle should be and how it ought to break apart. When the real particle is measured, its true mass and behaviour become a direct test of whether that picture holds. This is why having two such particles is so valuable. The new one, with two charm quarks and a down, has an older sibling found nearly a decade earlier, identical except that its light quark is an up instead of a down. The two differ by that single swap, one light quark exchanged for another slightly different one. By comparing them carefully, physicists can watch how the strong force responds to that small change, holding everything else fixed. It is as close as this field comes to a controlled experiment, two natural objects that vary in just one way. The comparison feeds into a deeper question about matter itself. Ordinary protons and neutrons get most of their mass not from the quarks inside them, but from the sheer energy of the strong force binding those quarks together. The quarks themselves are surprisingly light. The force between them holds so much energy that, by the rule tying energy and mass together, that energy shows up as most of the particle's weight. In a sense, you and everything around you are heavy mostly because of the ferocious energy of the glue inside your protons, not because of the tiny quarks it holds. Studying doubly heavy particles helps physicists untangle how much of a particle's mass comes from its quarks and how much from the binding energy. There is also the plain matter of confirming that nature works as expected in a new corner. Every particle with two heavy quarks that gets found and measured is a place where the theory of the strong force could have gone wrong and did not, or, more interestingly, might yet. So far, these heavy cousins of the proton have fit the broad expectations, but the measurements are young, and the details, the exact masses, the ways the particles decay, are still being pinned down. Each number is a small verdict on a difficult theory. None of this would be possible without a machine that makes charm quarks in vast numbers and detectors sharp enough to catch the fleeting particles they form. The new discovery leaned on both, the abundance of the beams and the freshly upgraded eye watching them. It sits at the meeting point of raw production and fine measurement, which is exactly where the collider does its best work. Behind all of it stands the strong force itself, the glue that binds every quark into every hadron, and that never lets a single quark go free. That force is strange enough to deserve a chapter of its own, and it is where we turn next. The strong force is the most powerful of the four forces of nature, and also the most peculiar. The other forces we meet fade with distance. Pull two magnets apart and their attraction weakens the farther they get. Gravity between two objects grows feeble as they separate. The strong force does something almost opposite, and that single strange trait shapes everything about how quarks behave and why we can never catch one alone. The force is carried by particles called gluons, named for their role as glue. Gluons pass between quarks and bind them together, much as photons of light carry the electric force between charged particles. But gluons have a habit that photons do not. They interact with one another as well as with the quarks. Light rays pass through each other untouched, but gluons grab hold of gluons. That self-gripping is the root of the strong force's strange behaviour, and it makes the force far harder to calculate than the others. Here is the peculiar part. When two quarks sit very close together, the strong force between them is surprisingly gentle, almost as if they were nearly free. But try to pull them apart and the force does not weaken with distance the way you would expect. It stays strong, or even grows, as though the two quarks were joined by an elastic band that only pulls harder the more you stretch it. This is why a quark is never found on its own. To separate it fully from its partners would take an unlimited amount of effort, and nature has an escape hatch long before you get there. The escape hatch is where new particles come from. As you strain to pull two quarks apart, you pour energy into the stretching band between them. At some point, that energy becomes so great that, by the familiar rule linking energy and mass, it is cheaper for nature to conjure a fresh quark and antiquark out of the energy than to keep stretching. The band snaps, and new quarks appear at the broken ends, each capping off into a new particle. So instead of ever holding a lone quark, you end up with more hadrons. Quarks stay locked away, always, behind this trick. Physicists call the imprisonment confinement. This is exactly what happens in the debris of a collision. When a high-energy quark or gluon flies out of a crash, it cannot travel alone. As it races away, the strong force keeps snapping fresh particles into being along its path, and the single quark blossoms into a tight, narrow spray of hadrons, all flying in nearly the same direction. Physicists call such a spray a jet. When a detector sees a jet, it is really seeing the footprint of a single quark or gluon that was flung out of the collision, dressed up in a shower of ordinary particles by the strong force. The theory that describes all of this is written down and trusted, but its self-tangled nature makes it brutally hard to compute with. In many situations, there is no clean way to work out the answer with pen and paper. Instead, physicists turn to enormous computer simulations, chopping space and time into a fine grid and grinding through the calculations step by step. These simulations can predict the masses of particles and the strength of the force, and they match experiment impressively well, but they cost great effort and cannot easily reach every question. That difficulty is why every new hadron matters so much, and why the collider's steady output of them is so useful. Each one is a real answer that the tangled theory must be made to reproduce, and the strong force does more than bind single hadrons. Push matter hard enough, and the glue itself can be torn loose, melting quarks and gluons into a state that filled the newborn universe. That extreme state is where we go soon, but first a deeper asymmetry, hidden in matter itself. There is a puzzle so basic that it is easy to walk past, and yet it may be one of the deepest the collider studies. The puzzle is simply this. The universe is made of matter. You are, the ground is, the stars are, and as far as we can tell, there is almost no antimatter anywhere in it. That sounds unremarkable until you learn what the theory says should have happened at the beginning, which is that matter and antimatter should have been made in equal amounts, and then destroyed each other completely, leaving nothing behind. Antimatter is not science fiction. It is a real and well-understood part of nature. For nearly every particle of matter, there exists a mirror image partner, an antiparticle, with the same mass but opposite electric charge. The electron has the positron, the proton has the antiproton, and so on. Antimatter is made routinely in laboratories and even by ordinary radioactivity. It behaves in most ways like a reflection of ordinary matter, obeying the same forces and the same rules, just with certain signs flipped. The trouble comes when matter meets antimatter. When a particle meets its antiparticle, the two annihilate. They vanish, their mass converting entirely into a burst of energy, usually light. Nothing solid is left. This is not a rare or exotic reaction. It is what antimatter does the instant it touches ordinary matter, which is why antimatter is so hard to keep around, and why the universe cannot hold both in the same place for long. Now put those two facts together. If the early universe made matter and antimatter in perfectly equal amounts, then every particle should have found an antiparticle to annihilate with. The whole cosmos would have flashed into light and then faded, leaving a universe of radiation and no substance at all. No atoms, no galaxies, no planets, no observers. That is what balance would have produced. And yet here we are, made of matter, in a universe that plainly kept some of its substance. So something must have tipped the scales, ever so slightly, in favour of matter. The leading idea is that the early universe did not treat matter and antimatter quite symmetrically. If, for every so many billion antiparticles there were 1,000,000,001 particles, then almost everything would still annihilate, but a tiny surplus of matter would survive the Great Cancellation. That thin remainder, roughly 1 part in 1,000,000,000, would be everything we see. All the matter of every star and galaxy would be the leftover crumb after an almost perfect mutual destruction. For this to work, matter and antimatter must behave differently in some small way, breaking the mirror symmetry between them. Physicists call this difference a violation of a symmetry they label with the letters C and P, and the effect is real. It has been seen in experiments, first decades ago in other particles, and it is built into the standard model in a limited form. The theory does allow matter and antimatter to differ slightly, which is a genuine success. The catch is that the amount of difference the standard model provides appears far too small to explain the enormous surplus of matter we actually see. That gap is a live problem, and it is one the collider was well placed to probe. The beauty quark experiment in particular was built partly to study exactly how matter and antimatter differ in the decays of heavy particles, measuring the small asymmetries with great care. Where the differences are larger than expected, or arise where they should not, they could point past the standard model toward the missing piece. Watching matter and antimatter disagree in fine detail is the work of the next chapter. To hunt for the difference between matter and antimatter, physicists watch how heavy, unstable particles fall apart. The beauty quark experiment is built for this. It produces enormous numbers of particles containing bottom quarks and charm quarks, along with their antimatter versions, and then compares them. The question, asked over and over, is simple. When a particle decays one way, does its antimatter mirror decay the same way, at the same rate, into a mirror set of products? If the two differ, matter and antimatter are not perfect reflections after all. For a long time, this kind of difference had been seen only in particles built from certain quarks, first in one family decades ago and later in others. A milestone came when the beauty quark experiment observed the same asymmetry appearing in particles containing charm quarks, a place it had never been clearly seen before. The effect was tiny, a small imbalance between how the matter and antimatter versions decayed, but it was real and measured carefully. Each such observation extends the reach of the known asymmetry into new corners of the particle world. More recently, the experiment pushed the search into heavier 3-quark particles, the baryons, looking for the same kind of matter-antimatter difference in how they break apart. Finding it there, in particles that are close relatives of the proton, is significant, because the proton and its kin are what ordinary matter is made of. If matter and antimatter differ in the behavior of such particles, it brings the study closer to the everyday stuff that actually survived the early universe. These measurements are delicate, demanding huge numbers of collisions to see a small effect clearly, and they are exactly the kind of work the experiment was designed for. The results, taken together, tell a consistent and slightly frustrating story. Matter and antimatter really do differ, in just the ways the standard model allows, and the measured differences have largely matched what the theory predicts. This is a genuine triumph for a theory built decades ago. It anticipated that these asymmetries would exist, and roughly how large they would be. An experiment keeps confirming it. The mirror between matter and antimatter is indeed slightly cracked, and the theory described the crack correctly. The frustration is that the crack, as the standard model describes it, is nowhere near wide enough. The amount of matter-antimatter difference the theory provides falls far short of what would be needed to leave behind all the matter in the universe. By the theory's own accounting, the early cancellation should have been far more complete than it apparently was, leaving far less matter than we find. So while every measurement confirms the theory in detail, the theory as a whole still cannot explain why there is a universe of substance at all. Something is missing. That missing something is one of the prizes physicists hope to find. Somewhere, they suspect, there must be an additional source of matter, antimatter difference beyond what the standard model contains, some new particle or force that tipped the early balance more sharply. The collider's precise measurements of these tiny asymmetries are one of the main places such a new effect might reveal itself, showing up as a difference larger than the theory allows, or appearing where the theory says it should not. So far, the measurements have stayed stubbornly within the theory's bounds, offering no clear breach, but the search is patient, and precision keeps improving. Each finer measurement narrows where a new effect could hide. This is a recurring shape in the collider's story. The theory keeps passing its tests, even as everyone knows it cannot be the whole answer. There are, however, extreme conditions the machine can create where matter behaves in ways no ordinary experiment can reach, and one of them recreates the first instance of the universe itself. For most of its runs, the collider smashes protons together, but a few times each year, it does something different. It fills its beams with a nuclei of lead atoms, each one a dense bundle of protons and neutrons far heavier than a single proton, and sends those crashing into each other instead. When two lead nuclei collide head-on at nearly the speed of light, the result is not one small burst but a violent crowded fireball, and inside that fireball matter is pushed into a state unlike anything in ordinary experience. Under such extreme heat and density, the protons and neutrons themselves cannot survive. Ordinarily, quarks are locked inside their hadrons, held by the strong force that never lets them roam free. But in the fireball of a lead collision, the temperature climbs to trillions of degrees, hotter than the core of any star, and the confinement breaks down. The quarks and the gluons that bind them are set loose, no longer trapped in separate particles but swimming together in a single hot soup. Physicists call this state the quark-gluon plasma. This is thought to be the state of the entire universe in its very first instance, a tiny fraction of a second after the Big Bang, before things had cooled enough for quarks to settle into protons and neutrons. For that reason, a lead collision is sometimes called a little bang. It is a way of reaching back for the briefest flicker to conditions that have not existed naturally since the universe was newborn. The collider cannot travel in time, but it can, in one small spot, briefly remake the heat of the beginning. The experiment built to study this is the one named Alice, tuned specifically for the chaos of heavy collisions. Where a proton crash produces a manageable spray of particles, a lead crash produces thousands of them at once, pouring out of the fireball in a dense flood. A detector designed for the cleaner proton events would be swamped. Alice is built to keep track of that flood, to identify the many particles streaming out, and to read from them what the plasma was like in the instant before it cooled and froze back into ordinary matter. The plasma itself does not last. It exists for an almost unimaginably short time, expanding and cooling in far less than a trillionth of a second, and then the quarks and gluons recombine into ordinary hadrons that fly out to the detector. Physicists never see the plasma directly. They study it the way one might study an explosion by examining the fragments, reading the pattern of outgoing particles to reconstruct the fleeting hot droplet that produced them. From those patterns, a surprising picture of the plasma has emerged. Recreating the first instant of the universe sounds like the boldest possible claim, and it is worth stating honestly what is and is not meant. The collider does not reproduce the whole Big Bang, only a particular hot, dense state that the early universe is thought to have passed through. It does so in a spot smaller than an atom, for a flicker of time, and only by inference. But within those honest limits, it is a genuine echo of the beginning, a way to test our ideas about the newborn cosmos against something we can actually make and measure. What the plasma turned out to be surprised nearly everyone. Physicists had expected the freed quarks and gluons to behave like a thin gas, a loose swarm of nearly independent particles. Instead, the plasma behaves like a liquid, and a very particular kind of liquid at that. Understanding just how strange that liquid is and what its behavior reveals is where we turn next. When physicists first set out to make the quark-gluon plasma, most expected a gas. Free the quarks and gluons from their hadrons, the thinking went, and they would fly about loosely, barely touching. like the molecules of the air in a room. What the experiments found instead was a liquid, and not an ordinary one. The plasma flows. It behaves like a fluid so smooth and so free-flowing that it turned out to be, by a certain measure, the most perfect liquid known in nature. The measure in question is viscosity, which is just a fluid's inner stickiness, its resistance to flowing. Honey has high viscosity and pours slowly. Water has much less and flows freely. The quark gluon plasma has less still, so little that it comes remarkably close to a theoretical flaw, a lowest possible stickiness that the laws of physics seem to allow. It is the least viscous fluid ever measured, a liquid that flows more freely than any other substance we know, despite being hotter and denser than the heart of a star. Physicists read this from the way the fireball expands. When two lead nuclei collide slightly off-center, the overlap between them is not round but almond-shaped. A gas would expand outward evenly, forgetting that lopsided start. A liquid, flowing as a connected whole, carries the memory of that shape into the pattern of particles that stream out, pushing harder along the short direction of the almond than the long one. The detectors see exactly this lopsided flow in the outgoing particles, and its details reveal a fluid of astonishingly low viscosity, moving almost as a single connected thing. There is a second, striking probe of the plasma, and it involves the jets we met earlier. Sometimes a collision produces a very high-energy quark or gluon that goes tearing off, blossoming into a narrow spray of particles, a jet. In a lead collision, that jet may have to punch its way out through the dense plasma before it can escape. And the plasma resists. It saps the jet's energy, so that a jet emerging from the fireball comes out weaker and more scattered than it went in, sometimes almost shattered. Physicists call this jet quenching, and it is a direct sign of how thick and interactive the plasma really is. The clearest picture comes when a collision makes two jets flying in opposite directions. If one of them is born near the edge of the fireball and escapes quickly, while its partner has to cross the whole plasma to get out, the two arrive at the detector badly mismatched. One is strong and sharp, the other drained and smeared. That lopsided pair is a fingerprint of the plasma's grip, a way of measuring how strongly the hot medium holds on to anything trying to pass through it. From such measurements, physicists map out the properties of a substance that vanished a fraction of an instant after it formed. All of this feeds back into understanding the strong force under conditions it almost never faces, the same force that confines quarks inside protons, when pushed to extreme heat and density, produces this nearly perfect liquid. Studying the plasma tests our theory of that force in a regime far from ordinary matter, and it connects particle physics to the story of the early universe, which passed through just such a state on its way to becoming the world of atoms. The plasma is one of the Collider's more spectacular products, a droplet of the newborn cosmos remade under a field in Europe. But not everything the machine reveals arrives in a violent fireball. Some of its findings are almost ghostly, carried by the faintest and most elusive particles known, particles that were caught at a collider for the very first time. That quiet surprise is where we go next. Of all the particles in the standard model, the neutrino is the shyest. Neutrinos have almost no mass, no electric charge, and they interact with matter so weakly that they pass through nearly everything as if it were not there. Trillions of them stream through your body every second, sent out by the sun, and you never feel a thing. A neutrino could fly through a wall of solid lead many light years thick and stand a fair chance of coming out the other side. They are the great ghosts of physics, everywhere and almost untouchable. Neutrinos are produced abundantly in the collider's crashes. Whenever certain heavy particles decay, neutrinos come flying out among the debris. But because they interact so weakly, the great detectors wrapped around the collision points barely notice them. A neutrino born in a collision usually sails straight through the layers of a detector without leaving a mark, carrying off some energy invisibly. For decades, this meant that although colliders made floods of neutrinos, no collider had ever actually detected one. They were made by the billion and caught not once. That changed with a small, clever experiment placed far down the tunnel from one of the main collision points. The idea was to sit in the path of the neutrinos streaming forward out of the crashes and put a dense, patient detector in their way, far enough downstream that the flood of other particles had been absorbed by rock and shielding, leaving mostly the ghostly neutrinos still travelling on. Given enough of them passing through a dense enough target, a rare few would finally interact and leave a trace. In the year 2023, that experiment announced success. It had detected neutrinos produced in the collider's collisions, the first time neutrinos had ever been caught at a particle collider of any kind. After decades of colliders making them unseen, a detector had finally pinned some down. The signals were unmistakable, the telltale tracks of neutrinos interacting inside the target standing out from the background. A ghost that had slipped through every previous machine had, at last, been recorded. The achievement matters for more than the thrill of a first. The neutrinos made in the collider are among the highest energy neutrinos ever produced in a controlled way on Earth, far more energetic than those from most other laboratory sources. Studying them opens a new window on how neutrinos behave at high energy, a regime that had been hard to reach. And it builds a bridge to astronomy, because the universe sends us neutrinos of even higher energy from violent distant sources, and understanding the collider's neutrinos helps make sense of those cosmic ones. There is a nice symmetry in the fact that a modest detector tucked to the side caught something the giant experiments could not. The great detectors are built to surround a collision and catch as much as possible, but their very design lets neutrinos slip through. It took a specialized instrument, placed exactly where the neutrinos would be streaming and shielded from the rest, to finally see them. It is a reminder that the collider is not one experiment but many, and that a clever small idea can catch what the giants miss. The neutrino, then, is one more piece of the world the collider has managed to grasp, a particle so faint it had eluded every machine of its kind until now. And the machine has reached even further into the strange, catching not just new particles, but a deep and counterintuitive feature of quantum reality itself seen at an energy no tabletop could dream of. That is where we go next. Some of the strangest behaviour in all of physics belongs to the quantum world, and one of the strangest features of all is entanglement. When two particles become entangled, their properties are linked in a way that has no everyday equal. Measure one, and you instantly know something about the other, no matter how far apart they have travelled. It is not that a message races between them. It is that the pair was never really two separate things with separate properties, but a single linked system that only reveals itself when measured. This is the feature that troubled even the founders of quantum theory. For most of its history, entanglement has been studied at low energies, using gentle particles like photons of light or slow electrons in careful laboratory setups. Those experiments confirmed, again and again, that entanglement is real and behaves exactly as quantum theory predicts. But they all lived in the same low-energy world, the tabletop realm of soft light and cool atoms. Whether entanglement would show up the same way at enormously high energies among the heaviest particles in the violence of a collider was a question that had gone almost entirely unexplored. The collider offered a way to ask it, using the heaviest fundamental particle known, the top quark. When the machine's collisions produce a top quark, they often produce it together with its antimatter partner, and the pair is born linked, their spins connected in the quantum way. If entanglement holds at these energies, the two should show correlations stronger than any ordinary unlinked pair could. Measuring those correlations would test entanglement in a wholly new setting, at an energy scale 1,000 billion times higher than the usual tabletop experiments. In the year 2023, the Atlas experiment reported that it had done exactly that. Studying pairs of top quarks and their antiparticles from earlier collisions, it found the strong correlations that entanglement predicts, and at a strength that ruled out an ordinary, unentangled explanation. It was the first observation of quantum entanglement between a pair of quarks and the highest energy observation of entanglement ever made. The result was published the following year, and the rival CMS experiment soon confirmed it with its own measurements. Two independent teams once again saw the same strange thing. How they managed it is elegant, and it hinges on the top quark's peculiar nature. The top quark is so heavy that it is extraordinarily unstable, decaying almost the instant it forms, far too quickly to bind up with other quarks the way lighter quarks do. In that swift decay, it passes its quantum properties, including the orientation of its spin, onto the lighter particles it becomes. By carefully measuring the directions of those decay products, physicists can read off the spin of the parent top quark. No other quark allows this, because the others get locked away inside hadrons before they can be read. What makes this more than a curiosity is where it points. It shows that the collider can serve as a laboratory for quantum information itself, testing the foundations of quantum mechanics in a regime no one had reached. Ideas and tools borrowed from the study of quantum computing can now be brought to bear on particles at the highest energies, and, running the other way, the behavior of these high-energy particles might one day expose some subtle crack in quantum theory, or in the standard model that gentler experiments would miss. A door has been opened, and the view through it is only beginning. The top quark keeps appearing at the centre of these stories, the heaviest and most fleeting of the quarks, and it deserves a closer look on its own terms. Why it is so heavy, why it dies so fast, and why that makes it so useful is where we go next. Among the 6 kinds of quark, the top quark stands apart for one plain reason. It is enormously heavy. A single top quark weighs about as much as an entire atom of gold, which is staggering for something that is supposed to be a fundamental point-like particle with nothing inside it. It is by far the heaviest of the quarks, and the heaviest fundamental particle of any kind that we know. Why it should be so much heavier than its fellow quarks is not fully understood, and that mystery is part of what makes it interesting. That great mass has a dramatic consequence. The heavier a particle is, the more ways it generally has to decay, and the faster it tends to fall apart. The top quark is so massive that it decays almost immediately after it is born. In a time so short it is hard to write down in ordinary words, a small fraction of a trillionth of a second. It lives and dies faster than almost anything else in nature, vanishing into lighter particles before it has any chance to do what other quarks do. What other quarks do, remember, is bind. The strong force locks quarks away inside hadrons so quickly that a freshly made quark is dressed up in a shower of other particles almost at once, hidden from direct view. But the top quark decays even faster than this dressing up can happen. It falls apart before the strong force has time to bundle it into a hadron. This makes the top quark unique. It is the one quark that lives and dies as something close to a bare, free quark, never sealed inside a larger particle. That single fact is what makes the top quark such a precious tool. Because it never gets locked inside a hadron, its properties are not smeared out or hidden by the binding process. When it decays, it hands its quantum traits, including its spin, straight to its decay products, cleanly and directly. Physicists can then measure those products and read the top quark's properties, almost as if they had examined the quark itself. With every other quark, the strong force gets in the way. With the top, there is a clear line of sight. This is exactly why the top quark was the right choice for studying entanglement, and it is why it serves as a sharp probe in many other measurements too. Its mass and its clean, swift decay make it a kind of window into physics that other particles obscure. Because it couples so strongly to the Higgs field, being the heaviest particle, it is also a sensitive place to look for any deviation in how the Higgs behaves, and a natural spot for new, undiscovered effects to show themselves if they exist. The top quark was itself a hard-won discovery, found at an earlier collider across the ocean before the Large Hadron Collider existed. But the Large Hadron Collider produces top quarks in far greater numbers than any machine before it, so many that physicists sometimes speak of a top quark factory. That abundance is what allows the delicate measurements, like the entanglement result, that need enormous numbers of clean events to draw out a subtle effect. A rare particle becomes a precision instrument once you can make it in bulk. So the top quark sits at the heart of some of the collider's finest work. A particle heavy enough to be strange and fleeting enough to be honest, telling its secrets before the strong force can hide them. It is also one of the places physicists watch most closely for the first sign that the standard model is incomplete, and there are hints, faint but persistent, that somewhere in the fine details the model may finally be starting to strain. Those hints are where we turn now. For all its triumphs, the standard model is known to be incomplete, and physicists have spent years searching for the first clear place where it breaks. Most searches have come up empty, with the theory passing test after test. But in the collider's later years, a set of measurements began to hint, faintly, at something that did not quite fit. The hints came from studying certain very rare decays of particles containing bottom quarks, and the story of those decays is worth telling carefully, because it is a story still unfinished. The decays in question are ones the standard model says should be extremely rare. In them, a bottom quark transforms into a lighter quark while emitting other particles, but only through a roundabout, deeply suppressed process. Physicists have long given this class of decays a whimsical name, calling them penguin decays, after a bet and a drawing made decades ago. The name stuck, and it now marks some of the most sensitive tests in the field. Because the decays are so rare in the standard model, they're a quiet place where a new unknown particle could leave an outsized fingerprint. The idea is subtle but powerful. Even a heavy new particle far too massive for the collider to make directly could still influence these rare decays, nudging them to happen a little more or less often, or to produce their debris at slightly different angles than expected. The tiny standard model contribution acts like a still pond, in which even a small ripple from something new would show. This is why physicists watch penguin decays so closely. They are indirect windows onto particles that might otherwise be out of reach, a way of sensing the heavy and unseen through their faint effects. In studying these decays, the beauty quark experiment found behaviour that did not fully match the theory's predictions. The rates and patterns of certain rare bottom quark decays came out somewhat askew from what the standard model said they should be. Taken together, a number of these measurements pulled in the same direction, building into what the physicists described as some of the strongest hints yet that there might be physics beyond the standard model hiding in the data. If the pattern held up, it would mean unknown particles or forces were subtly shaping the decays. It is essential to be honest about what this is and is not. These are hints, not a discovery. The disagreements with the theory are real but modest, and they have not crossed the strict 5 sigma line that a genuine discovery demands. The history of the field is full of promising anomalies that grew fainter as more data arrived, and in fact one earlier set of related hints, involving how these decays produce different lightweight particles, weakened considerably when examined more carefully. Caution here is not timidity. It is the hard-learned lesson of a field that has been fooled before. There is also a real difficulty in the theory itself. To claim that a measurement disagrees with the standard model, you must know precisely what the standard model predicts, and for these decays the prediction is hard to pin down. It depends on the tangled strong force, whose effects are notoriously difficult to calculate. Part of the ongoing debate is whether the apparent disagreement points to genuinely new physics, or whether it reflects an underestimated difficulty in the theoretical prediction. Both possibilities are taken seriously, and untangling them is active work. Still, the hints are the most interesting thing on the horizon, precisely because a real crack in the standard model is what everyone has been hoping to find. If the anomalies survive and strengthen, they could be the first solid sign of what lies beyond. And there are specific new particles that could explain them, ideas with names of their own, waiting to see whether nature calls them into the story. Those possibilities are where we go next. If the hints in those rare decays are real, something new must be causing them, and physicists have candidates in mind. The leading idea centers on a hypothetical particle with an unusual job. In the standard model, matter comes in two broad families that never mix in a certain way. There are the quarks, which feel the strong force and build protons and neutrons, and there are the lighter particles like the electron, which do not. The proposed new particle would bridge that divide, interacting with both families at once. Because it would tie quarks to those lighter particles called leptons, physicists have given it a fittingly blended name, the leptoquark. A leptoquark, if it existed, could naturally produce the kind of anomaly seen in the rare decays. By quietly influencing how a bottom quark transforms, it could nudge the rates and patterns of those decays away from the standard model's predictions, in roughly the way the data seem to hint. This is part of why the anomalies drew such interest. They do not just say the theory might be wrong, they point, if taken at face value, toward a specific and rather elegant kind of new physics, one that theorists had already imagined for other reasons. Leptoquarks are not the only possibility. There are many proposed theories that could account for the hints, some involving new force-carrying particles, others invoking richer structures beyond the standard model. The honest situation is that a range of ideas could fit the current data, and there is no way yet to tell which, if any, is correct. The anomalies are suggestive but not decisive, and the space of explanations is wide. Building a new theory to match a hint is easy. Knowing that the hint is real, and that the theory is right, is far harder. There is a deeper reason these indirect searches matter so much, and it has to do with reach. A new particle like a leptoquark might be far too heavy for the collider to create directly, beyond the energy the machine can muster, yet through its faint influence on rare decays, it could still betray its existence. This has happened before in the history of physics. The particles behind a well-known form of radioactivity were sensed through their effects long before any machine could produce them directly, decades passing between the first indirect signs and the eventual direct sight. Rare decays let physicists probe energies they cannot yet reach head-on. Some of the new particles hinted at in these studies may lie so far out of reach that no machine now planned could make them, only colliders imagined for the distant future. That is a sobering thought and also a motivating one. It means that careful measurement of rare, delicate processes may be, for a long time, the only way to sense what lies at those extreme energies. The patient study of penguin decays is not a lesser kind of physics than making a new particle outright. In some cases, it may be the only kind available. For now, everything hangs on whether the hints survive. More data and better theoretical calculations will either sharpen the anomalies into something undeniable, or wear them back down into agreement with the standard model. Both outcomes have happened to earlier hints, and there is no telling in advance which way these will go. The next great run of the machine, once it is rebuilt, is where the question may finally be settled, one way or the other. It is worth remembering too that alongside these tantalizing hints stands a long list of things the collider looked for and did not find. Those empty-handed searches are not failures, and understanding why is important. The absence of a discovery can be as informative as its presence, and that is where we turn next. Not every search ends in a discovery, and most of the collider's searches did not. For years, physicists hunted through its collisions for a whole catalogue of proposed new particles, heavy and exotic objects predicted by theories meant to extend the standard model. They looked for signs of hidden extra dimensions of space, for a proposed doubling of all the known particles, for new heavy force carriers, and for particles that might make up the universe's invisible matter. In case after case they looked hard, and they found nothing. The expected new particles did not appear. It is tempting to hear that as failure, but it is not, and the reason is worth understanding. When a search for a new particle comes up empty, it does not simply leave a blank, it sets a limit. It tells the theorist that if such a particle exists at all, it must be heavier than a certain amount, or interact more weakly than a certain strength, because otherwise the collider would have made it and seen it. Every empty search shrinks the space where the unknown can still be hiding. The map of what is not there is itself a kind of knowledge, and a valuable one. Those limits have real consequences for the theories physicists take seriously. Many proposed extensions of the standard model predicted new particles light enough that the collider should have produced them. When the machine ran and those particles failed to show, the simplest versions of several popular theories were ruled out or pushed into ever more cramped corners. Ideas that had been fashionable for decades had to be reconsidered or abandoned. That is painful for the theories, but it is exactly how science is supposed to work. Nature is allowed to say no, and here it said no repeatedly. There is a particular sting in this for one long-cherished idea, a proposed symmetry that would have paired every known particle with a heavier partner. That idea had elegant reasons behind it, and had been expected by many to reveal itself at the collider's energies. It offered a tidy solution to several puzzles at once, including a candidate for the invisible matter of the cosmos. But its predicted partner particles did not appear, at least not in the mass range the collider could reach. The theory is not dead, since its partners could simply be heavier than the machine can make, but the easy, hoped-for version of it did not come true. Living with null results is part of the discipline of the field. It would be easy, facing search after empty search, to grow discouraged, or worse, to start seeing signals in the noise out of sheer longing. The strict 5 sigma standard and the habit of blind analysis exist precisely to guard against that. They keep physicists honest when hope runs high and evidence runs thin, a field that only ever announced discoveries and never reported the many searches that found nothing would not be doing science at all. The empty results are the quiet backbone of the whole enterprise, and the empty searches sharpen the question rather than closing it. The collider has now told us with great precision many places where new physics is not. That focuses attention on the places where it still might be, including the faint anomalies in rare decays and the corners at higher energies or weaker couplings that the machine could not quite reach. The next, more powerful version of the collider is aimed partly at those remaining corners. One of the most important things the collider searched for and did not clearly find is also one of the most abundant things in the universe, a form of matter that vastly outweighs everything we can see and yet has never been directly caught. That great invisible presence is where we turn next. Look up at the night sky and everything you see, every star, every distant galaxy, every glowing cloud of gas adds up to only a small slice of what is out there. Astronomers have found, over decades, that the visible matter of the universe, the ordinary stuff made of atoms, accounts for only about 1/20 of everything. The rest is invisible, and it comes in 2 kinds. One is called dark matter, and the other dark energy. And together they make up the overwhelming majority of the cosmos, while the matter we know is a thin garnish on top. Dark matter announces itself through gravity. Galaxies spin faster than the visible matter within them could explain. Clusters of galaxies hold together more tightly than their glowing contents should allow. The light from distant objects bends around unseen masses. Everywhere astronomers look, there seems to be far more gravitating matter than there is visible matter to account for it, several times as much. Something is there, exerting a pull and giving off no light we can detect. That something is dark matter, and by weight it dwarfs all the ordinary matter in the universe. The trouble is that no one knows what it is made of. It is not made of ordinary atoms, and it does not fit anywhere in the standard model. The leading guess for many years was that dark matter consists of some new kind of particle, one that has mass and feels gravity, but barely interacts with ordinary matter in any other way, which would explain why it has never been directly seen. If such a particle existed and was not too heavy, then a machine like the collider, which turns energy into new particles, might be able to make some. So the collider joined the hunt. Physicists reasoned that if dark matter particles were produced in a collision, they would slip out through the detectors unseen, just as neutrinos do, carrying away energy and momentum invisibly. The trick would be to add up everything that came out of a collision and notice if some energy had gone missing, spirited away by an unseen particle. A collision that looked lopsided, with a visible spray on one side and nothing to balance it, could be the signature of dark matter escaping the detector. The experiment searched for exactly this, event after event, for years, and they did not find it. No clear sign of dark matter production emerged from the collisions. As with the other empty searches, this did not leave a blank but a limit, narrowing the range of masses and interaction strengths that a dark matter particle could have and still have escaped notice. The simplest and most hoped-for versions of the dark matter particle, the ones that would have been easiest to make, did not appear where they were expected. This does not mean dark matter is not real. The astronomical evidence for it is strong and comes from many independent directions. It means only that dark matter, if it is a particle, is not the particular kind the collider could most easily have made, or that it interacts even more feebly than hoped. The mystery remains one of the largest in all of science. Most of the matter in the universe is of a kind we cannot identify, and the most powerful machine ever built for the job has, so far, not caught it in the act. That unfinished hunt is one of the strongest reasons the collider is not being retired but rebuilt. To reach the fainter signals, the rarer events, the corners it could not quite touch, the machine needs to be more powerful still. Why a working collider is being taken apart to make it stronger is the story of the next chapter. It may seem strange to switch off a machine that is still working and finding new things. Yet on the last Monday of June, in the year 2026, that is exactly what happened. The collider had just finished its third long run of collisions, having spent years gathering data and turning up discoveries right to the end, including that heavy new cousin of the proton only months earlier, and then it was deliberately shut down to begin a planned pause that its operators call Long Shutdown 3. The stop was not a defeat, but a step in a long-laid plan. The reason is that the collider, for all its power, had reached the limits of what its current form could do. Many of the most interesting questions left, the fine details of the Higgs, the faint anomalies in rare decays, the search for dark matter and other rare signals, all demand something the machine could not provide in its present state, which is simply more collisions. The rarest and most subtle effects show up only in enormous piles of data, and to gather those piles in a reasonable time, the machine has to be made to collide far more often than it does now. That is what the shutdown is for. Over roughly 4 years, crews will rebuild large parts of the collider and its experiments to prepare a far more powerful version. The work is enormous. About 1.25 kilometers of the ring's magnets and components will be pulled out and replaced with new equipment, including new superconducting magnets able to squeeze the beams more tightly than before. Squeezing the beams harder packs the protons closer at the collision points, so that far more of them meet each time two bunches cross. This is the most extensive intervention on the machine since it was first built. The pause is not only about the Great Ring. The whole chain of smaller machines that feeds it, the experiments themselves, and much of the supporting infrastructure will all be upgraded or renewed at the same time. Thousands of specialists from the laboratory and from partner institutions around the world will take part. Sections of the machine that have been sealed and cold for years will be opened, worked on, and closed again. The cost of the upgrade runs to well over 1 billion Swiss francs, shared among the many countries that support the laboratory, with contributions of parts and labour from around the globe. All of this takes time, which is why a shutdown is measured in years. The great magnets cannot simply be switched off and touched. They must first be warmed slowly from their deep cold, near the lowest temperature there can be, up toward room temperature, a process that itself takes weeks. Then the physical work of removal and replacement can begin, and afterward everything must be cooled back down, tested, and carefully brought back to life. A machine this large and this delicate cannot be rushed, and the years of the shutdown are packed with painstaking labour. There is something quietly moving in the decision to do all this. The people who run the collider are not content with the discoveries it has already made, remarkable as they are. They are willing to take a working, productive machine offline for years at great cost and effort on the conviction that the questions still open are worth the wait. It is a bet on the future, a choice to build toward answers that the present machine could never reach, however long it ran. When the work is finished, Near the end of the decade, the collider will return transformed, able to make collisions at a rate many times higher than before. What that more powerful machine is meant to do, and what it might finally find, is where we turn next. The rebuilt machine has a name that says exactly what it is for. It will be called the High Luminosity Large Hadron Collider, and luminosity in this context is simply a measure of how many collisions the machine produces. Raising the luminosity means packing the protons more tightly and crossing the beams more often, so that far more collisions happen in the same span of time. The upgraded machine is designed to reach a luminosity up to 10 times higher than the collider was originally built for. 10 times the collisions means, over the years, many times the data. The difference this makes is best seen in the numbers for the Higgs boson. Across all its years of running, the collider produced something like 55 million Higgs bosons, enough to confirm the particle and check its broad behaviour, but not enough to catch small deviations in its rarest habits. The upgraded machine is expected to produce far more, on the order of several hundred million Higgs bosons over its lifetime, many times the earlier harvest. With that many, physicists can measure the Higgs with a precision the current data cannot approach, and any small crack in its behaviour would have a chance to show. One prize in particular is out of reach now, but within hope for the upgrade. Physicists want to see two Higgs bosons produced together in a single collision, and then watch them interact with each other. This double production is so rare that the collider has barely glimpsed it, far too seldom to study. The upgraded machine's flood of collisions could finally make it observable. Watching how one Higgs affects another would test a deep and unproven part of the theory, the way the Higgs field interacts with itself, which is tied to how the universe settled into its present state after the Big Bang. More collisions also mean more chances to make anything rare, which is why the upgrade matters for every open question we have met. The faint anomalies in rare decays could be sharpened into something undeniable, or worn away, once far more of those decays have been collected. The searches for dark matter and for other new particles gain reach, able to probe fainter signals and rarer events than before. The measurements of matter-antimatter differences grow more precise. The whole program of the machine is lifted by the simple fact of having far more data. There is a challenge hidden in this abundance, and it is a peculiar one. When collisions happen this often, so many occur at once, packed into each crossing of the beams, that the detectors face a far messier picture than before. Instead of a handful of collisions per crossing, there may be well over 100 piled on top of one another, their debris overlapping in a tangle. Sorting out which particle came from which collision becomes far harder. To cope, the experiments are being upgraded too with new components, and the physicists are turning increasingly to artificial intelligence to help pick the interesting events out of the flood in real time. The upgraded machine is expected to begin running near the end of the decade, after the years of the shutdown are done, and then to keep running for many years beyond that, well into the following decade. It is a long horizon, the kind that outlasts careers, and it reflects how patient this science has become. The great questions do not yield to a single run. They are approached slowly, over decades, by a community that keeps building better tools and handing them to the next set of hands. So the collider is not ending. It is pausing to become something more, and its most productive years may still lie ahead. Which brings us back at last to the quiet ring where we began, and to what it means to keep asking. We began in a silent tunnel in the early summer of the year 2026, with the largest machine ever built newly at rest beneath the fields near Geneva. Now, having gone down into that ring and looked at what it holds, we can return to the quiet with a fuller sense of what has actually gone still. It is not merely a machine that has paused. It is a way of asking the oldest questions, put on hold for a while so that it can be made to ask them better. Think back over what the collider found inside itself. It caught the ripple in an invisible field that gives matter its mass, a particle waited on for half a century. It broke the old rule that quarks come only in 2s and 3s, turning up a growing family of exotic particles no one had held before. It added more than 80 new pieces of matter to the known catalogue, including, in its final months, a heavy new cousin of the proton. It recreated, in a spot smaller than an atom, a droplet of the newborn universe, and found it to be the most perfect liquid known. It caught the ghostly neutrino where no collider had before, and it saw the strange linkage of entanglement at an energy no tabletop could reach. And it did something quieter, but just as important. It kept the wonder honest. Where it searched for hoped-for particles and found nothing, it said so, and turned those empty searches into real limits on what can exist. Where it found faint hints of a crack in our best theory, it named them as hints and no more, resisting the pull to announce a discovery before the evidence had earned it. The machine's greatest discipline was not in what it claimed, but in what it refused to claim, and that restraint is what makes its real findings trustworthy. The title we started from promised that no one was ready for what the collider found, in a way that is true, though not in the way a headline means it. There was no single hidden secret waiting to be cracked open. Instead, there was this steady stream of the genuinely new, handed over one collision at a time, so much of it that even the people who built the machine are still working through what it all means. The surprise is not one shocking thing. The surprise is how much strange real world was packed into those tiny crashes, and how patiently it had to be drawn out. That is perhaps the truest thing to carry away from the ring. The universe does not usually give up its structure in a single revelation. It yields it slowly, in fragments, to those willing to build the tools and do the patient, doubting work of measurement. A machine the size of a city, run by thousands of people across dozens of countries, spent years coaxing out pieces of an answer, and its reward was not a final truth but a handful of new and better questions. For now the ring rests, warming slowly from a cold deeper than deep space, waiting for the hands that will rebuild it. In a few years the beams will circle again, more crowded and more powerful than before, and the asking will resume. Somewhere in those future collisions may be the crack that finally opens the door past our present understanding, or another droplet of the beginning, or a particle no one has yet imagined. We do not know. That not knowing, held calmly, is the quiet engine of the whole endeavour. The machine sleeps, and the questions wait with it, patient as the dark,